Okay, so uh, previously, if for example there were two objects, let's say, moving towards each other, and after the collision they moved towards this direction for the sake of example, then we did these calculations based on the idea that momentum is conserved. So it was basically the law of conservation of momentum. We knew the mass of this object, we knew its velocity, we knew the mass, and we knew the velocity, but we did add one more concept to this, that was add the negative sign, because it was moving towards the left side. Similarly, both of these objects contributed to the momentum that was before the collision, that was initial momentum of the system, and after the collision, these two objects contributed to the system that was happening after the collision. So of course we also knew the mass, because the mass remains unchanged to the collision. The masses would remain the same, the velocities would change, and they would give you one velocity after the collision, and the other one would have to be found by you. So the idea behind all of this was the conservation of momentum. So when I say initial momentum is equal to momentum after the collision, this idea is the law of conservation of momentum, because we've established that even if the collision is elastic or even if it's inelastic, the momentum is a conserved quantity. Okay, but in this topic that we're going to do today, we're going to explore how every law of Newton, that ranging from first law to the second law to the third law, how can we discuss them in terms of momentum. Now momentum is the product of mass and velocity, but how can we look at these rules or these laws in the light of momentum? So if we want to look at the first law, let's say, that was about inertia, and that practically told you that the motion of an object would not change unless disturbed by an external force. So over here we can say that momentum of an object will not change or will remain conserved as long as an external force does not act upon it. Alright? So we can say, or we can speak about Newton's first law in terms of momentum as well. That unless, for example, an object is stationary, for example, you're sitting on your chair, you're not moving, right now your momentum is zero. So your body would try to maintain this state of momentum, try to make sure that it stays zero if or unless an external force is not applied on you or somebody tries to push you away from the chair. Similarly, if a car was already moving in this direction, then it would want to stay, or it would want to maintain its state of momentum unless there is an external force that tries to stop it or that tries to accelerate it. Even in that case, if an object, or if a force, for example, tries to slow down an object or tries to increase its speed, we will refer to that as a change of momentum. So in a balanced condition or in an unbalanced condition, both cases we can refer to these situations as that a force or an application of force may try to bring a change in an object's momentum. So previously what we were discussing was simple motion, that an object is at rest or moving. Now we have replaced that term as momentum. So because momentum, of course, the formula for momentum is mass into velocity, that is mass multiplied by velocity. So there is a change of speed, there is a change of motion involved in this. So if we talk about the momentum, we were actually talking about the speed or the motion of the object as well. So this is a better way of saying or talking about laws of Newton in terms of just referring to this as a state of motion. Alright, this is how we talk about the first law in terms of momentum. Now we're going to look at how we talk about momentum in second law, and there were going to be some derivation, some formula associated to that. So over here we're going to talk about Newton's second law in terms of momentum. Okay, one interesting formula in this case would be that we know that from the second law the formula for force was equal to ma, and from kinematics chapter we know that the formula for acceleration is v minus u over t. right? So let's replace this formula for acceleration in this equation and see what it gets us. So F is equal to mass into acceleration, that would be V minus U over T. Now let's try to multiply this mass with these two factors and let's see how it opens up. So we get mass into velocity minus mass into initial velocity divided by time taken for the process. That is equal to force. Now I would like to bring your attention towards this factor that we get in the numerator. What does that become? That basically becomes the change in momentum. How? This velocity is the final velocity, this u is the initial velocity. So final momentum minus initial momentum. So I can say that this is the change of momentum. So simply representing this as a mathematical quantity, I would write this down as delta, the symbol for change, the symbol for momentum, divided by the variable for time. Do we understand up to this point the derivation that is involved in this?
Yes.
All right. Now, the true understanding in terms of its advanced level idea of a force is this formula. This is how we define a force. A force, previously we understood the force as a factor that can bring about a few changes. It can change the shape of an object, and we did the chapter as deformation. It could change the motion of an object, as simply put F equals to ma, right? So this is how we looked at force. Or it can change, let's say, the direction of an object. In a circular motion object, the centripetal force causes the object to rotate, right? So this is how we actually looked at a force previously. Now we have concluded that force is actually a factor that can create a change in momentum of an object. That is what a force is defined in higher level physics. Now previously this concept was not a part of your course, but now it is, and partly because of the reason because momentum is a big part of A levels course. So what they did now is to combine the syllabuses of IGCSE and O levels 5054, so that eventually the students from both streams, when they merge into A levels, they won't feel a difference of chapters or of topics that they might not have studied before. So now everything in O levels is actually more about its alignment with the course that you're going to study eventually in A levels. Okay, so we understand that now the force will be defined as rate of change. Now I can also say that since this is being divided by time, I can say that force is basically rate of change of momentum. This is how I will define my force from now onwards. Okay, do we understand up to this point?
Yes.
All right. Now then what is F equals to ma? What is this equation? This is actually a special case of this same formula. But this case, what's so special about this is that the mass of the system does not change. So basically what's happening is that the formula is same, that is the rate of change of momentum, but the mass will not be changed. So where do we use this formula? As discussed previously, that there are cases in which the mass of the system may change during the motion. For example, as a rocket moves up into the space, it's using up its fuel very rapidly, so its mass is decreasing with the passage of time. So the value of acceleration would be changing at all times. So in those cases, we would have to use this formula to find out the average force exerted by the gas on the rocket as it moves from a lower level to a higher level, because at that situation, for example, if I consider the rocket to be at this location and I consider the rocket to be at this location, I can very well see that the masses of the rocket in these situations would be very different. And if I want to calculate the amount of force that was exerted as a result of all of these changes, then I would have to use this formula. And let's try to do that example right now for the case of a rocket. How does that work about? Let's say that the mass of the rocket over here was 50 kg when it was at a lower sky or at a lower height in terms of the earth. At this point, let's say that the mass of the fuel, since it is being used up, now the mass of the rocket and the fuel is 20 kgs. This whole task has been achieved, or you can say that this whole task took about, let's say, 10 seconds. 10 seconds to complete, right? And the velocity of the rocket at this location, let's say, was 5 meters per second, and at this location it was 20 meters per second. So we have all the necessary information over here that we can use in the formula. So let's put F is equal to change in momentum divided by the time taken for the process, right? So what's my final momentum? That is the final velocity multiplied by the final mass. That would be 20 into 20 minus my initial velocity and initial mass. That would be 5 multiplied by 50 divided by the total time for the process, that is time t, 10 seconds. That how we measuring this time? What we did was we started the stopwatch when the rocket crossed this hemisphere, and we stopped the stopwatch when it crossed this level. So the total time between these two instants, the time taken for the process would be 10 seconds. Okay, so let's move ahead and see how we're going to solve this. So what we get is 400 minus 250 divided by 10. So what we are left with is 150 divided by 10. So we have an average force of 15 newtons. Now I'm using the word average force. What is the reason for that? The reason for that would be there would be many instants between these two locations where the mass is basically decreasing every second by every passing time. So the amount of force will be changing at every instant as the speed with the passage of time. Let's say if I look at the formula for momentum, the speed would have been increasing and the mass would have been decreasing with the passage of time increasing as a result. So these three variables would be all time changing as this motion is taking place. I cannot calculate that for every instant, although I can, but it's a tiresome process. It's not worth it. So what we do, we find the average force. That okay, let's look at the scenario at the beginning of the motion, let's look at the scenario at the end of the motion, and let's assume that throughout the motion the rocket experienced a force of 50 newtons in the upwards direction, but in reality this would be a different case. Do we understand the idea? Do we understand this?
Yes, I understand.
All right. So for every little key moment, this value will be different. But we are not going to do that because it's not, you can say mathematically speaking, it doesn't get us any closer to all of this. But we do have a concept in mathematics that is known as integration and derivation. These two things, or these two mathematical procedures, basically give us the exact answer. How much force would the rocket would have experienced if we had included every tiny level? But that is a complex procedure that actually you will learn that in A levels. So up to this point in O levels, this is what where we draw the line, that this is what we are going to learn, and this is how we look at these things. So force now is defined as the change of momentum with respect to time, and not only F equals to ma, but this formula will also be used to calculate forces, or calculate force of the object that is experiencing some change in velocity or a change in mass with respect to time. So if we rearrange this formula, that is F is equal to change in momentum divided by time. If I bring this time over here, that would become force multiplied by time equals to change in momentum. This side of the equation, that is a product of force and time, and this side of the equation, that is known as the change of momentum, they are basically practically equal. But this time, the product of force and time has a special name. That name is impulse. And on the other hand, we observe change in momentum. So sometimes what the examiner does is refer to the situation, and he would ask you to find out the change in momentum, and the only quantities he would give you would be force and time. So it doesn't matter whether he's asking you about change in momentum, we know that it's equal to product of force and time. And if he's asking you about impulse, and he has given you values of mass and velocity before and after the collision, then that is fine. You can use them to find out the change in momentum, because impulse is equal to change in momentum, and change in momentum is equal to impulse. Both quantities are equal to each other. So sometimes the confusion he creates is he will use the name impulse, and although it is force into time, but he would give you the values of, mathematically, he will give you the values of mass and velocity. And sometimes in words he will use the word change in momentum, but in reality he will give you the values of force and time. So you don't need to be confused about that because both sides are equal to each other. So it doesn't matter the name of this side and the values of that side, or the name of this side and the values of that side, or the name of this side with the same values and the name of this side with the respective values. It can give you in any combination. The question shouldn't be any problem for us, or solving it shouldn't be any problematic situation for us. Do we understand the problem or the confusion that the examiner may create for you in this situation? Yes?
Yes.
All right.
So changing momentum in positive.
Okay, so this is how we look at Newton's second law in terms of momentum. Okay, so it's not only defined by force causing an acceleration, it is basically force causing a change of momentum. Now let's look at Newton's third law in light of momentum. Would you like to take a guess how we're going to define this over here? So the way we look at Newton's third law in terms of momentum is that the change of momentum for both objects will be the same but in the opposite direction. Now let's look at this example on a more universal scale, and let's try to make things interesting. For example, if we have an exploding object that is this way, and we know that when it eventually explodes, it's going to explode in this way. Let's say it's a star that is about to explode. Alright, so can you tell me what is the momentum of this object before it explodes? Its momentum is 0. Why? It does have some mass, but it's not moving before the explosion, so its velocity is approximately 0. So according to the law of conservation of momentum, it should remain the same before or after the collision or explosion, right? So if this object eventually does explode, it is going to initiate some massive objects in all directions like this. So some part of this object may end up going over here, some part of it, just the rubble or the dirt, maybe ending up in all these directions, eventually moving in these directions. Do you understand this idea? Yes? But if all these masses, the little masses that actually are a part of this one, are moving in these directions, then if I multiply with their respective velocities, their momentum will not be 0. But we said that the momentum before the collision or before this explosion was effectively 0. Then how is it possible that the momentum after the explosion is not 0? The way we look at this is that if this momentum or if this mass is moving towards the right side, then it's ultimately always going to be true that there is going to be some mass moving in the opposite direction that is actually cancelling out the momentum of this object. Do you understand what I'm saying over here? Right? So all these masses that are actually exploding and moving away from each other would have generated some momentum in the opposite direction, which eventually will cancel out. If I consider this whole system, the momentum after the collision would also become 0, or would also come down to 0. So, and the way to look at this would be that, for example, if you are standing on a skateboard, let's say, and you have a friend that is also standing on a skateboard, let's say, and you are stationary before anything happened. When you try to push on your friend who is standing on the other skateboard, your friend might start moving towards this direction. Where do you think you would be moving? You would be moving in the backwards direction, right? So although you applied the force in the right side, but you're moving in the back side. So what's actually happening is that the momentum that you created on the positive side has been compensated by your own momentum that is created on the negative side. Why? Because the momentum before you applied any force was 0. So according to the law of conservation, the momentum after any disturbance or after any problem that you might have created should also be 0. So if you created some momentum to the positive side, to make sure that it remains 0 overall, there should be some momentum in the negative direction. So when I add the positive momentum and the negative momentum, the overall answer should be 0. Do we understand this? And if I add this negative sign over here, because you're moving to the left side, then this becomes P minus P. If you take that over there, that becomes P is equal to P, which means that the momentum of your object and the momentum of the other object are effectively equal, but in the opposite direction. That is why the overall momentum would still be 0. Okay, so this is one more example. Let's say you're standing on the surface of the earth. Now let's say that you jump upwards. You're jumping upwards, but verily you applied a force downwards on the earth with your feet and your legs, and as a result you started moving upwards. Now before you jumped, your momentum combined with the Earth was 0. So even in this situation, the momentum after you made the jump in the opposite direction should also be 0. So if we look at very closely, theoretically speaking, the Earth would have gained some momentum in the opposite direction. But why don't we see the Earth moving in the other direction? Is because of its large mass. So let's say that the momentum of, let's say, the object that is the boy should be equal to the momentum of the Earth, because before the jump or before this, they were both standing in a complete harmony. There was no momentum. The momentum was 0. So the momentum of the boy, let's say, I say that the mass of the boy is 80 kgs, for example. The speed by which it moves upwards, for the sake of example, is, let's say, 10 meters per second, very instant of the jump. The mass of the Earth is 6 into 10 raised to power 24. That is a actual value. I've just memorized this for my convenience so that I can give an example to the students. You don't have to memorize it. Alright, so I see that there are going to be 24 zeros after 6, and no matter how big this value is, this is going to eventually become 0. So this becomes 800 divided by 6 into 10 raised to power 24, and this becomes the velocity of the object. And I know that if I calculate this, this is going to become some velocity into 10 raised to power, let's say, minus 20 or 21 or 22. Let's say it's going to be 21. So this is going to be the speed of the Earth moving downwards. So it's impossible to see such a small speed by our own eyes or our naked eyes, but we do believe that this is what's actually happening. So the momentum is universal. It's happening at all places. All the objects are exchanging momentum. Whatever objects are trying to exchange forces are basically exchanging momentums. Do we understand? You may remember that when we were doing pressure in gases, we talked about the fact that if this is the wall of the container, then a gas molecule moving towards the wall and then bouncing back. Do you remember about this idea? So when this molecule was in collision with the wall, how did it exert some pressure? Now we remember that the formula for pressure was force over area. Now where is this area? The area is this tiny bit where the molecule makes a contact with the wall. So we are not concerned about the area because we already know where it is. We are concerned about the force. Where is the force coming from? So let's simplify this, although this is happening at an angle, but let's simplify this. For example, a molecule comes straight ahead, collides with the wall, and then goes back. The mass of the molecule is not changing throughout the procedure, but what we see changing is the velocity of the molecule. Let's say that it doesn't lose any velocity during the collision. So first the velocity was positive and then the velocity is negative. So I understand that if it had to exert a force on the wall, it should have observed a change in momentum. And where do I see that happening? I see that happening over here. There is a change of velocity because there is a change in direction. So when I apply the formula for force now, I understand why there is a force, because there is a change of momentum. So I understand that there is going to be some mass into velocity minus mass into negative velocity. Why is that happening? This is the negative sign because of the formula. When I say change in momentum, I'm supposed to write down some momentum minus some final momentum, right? So that negative sign is because of the change, the formula of the change. And this negative sign is because of the velocity of the object. So when I see over here, of course, the divide by time is still a part of this equation. What I see over here is that this negative sign being cancelled by this negative sign, and what I'm left with is 2mv divided by t. And mind you, this is all ideally speaking, or ideal circumstances, that there is no change in velocity, there is no change in mass. And what is this time? This time is the time of contact. So if I slow this down, or I look at it from a tennis ball perspective thrown towards a wall, the time the tennis ball actually squeezes or actually gets squashed in its own weight or the force, and then expands back and then starts moving back towards you, the time of contact is what this time represents. So for how long the molecule was in contact with the wall, this is that time. And that is usually in milliseconds or probably in microseconds as well. So do we understand how a gas molecule may exert a force on the wall, and of course that the origin of that force is still the change of momentum of that individual gas molecule. Do you understand this? So these are all the ideas that the examiner expects from you as a student. What you may do is go through the book